In this tutorial, we're going to go over chemical kinetics practice questions. Just before we get to answer the questions that we have, let's get to review chemical kinetics. So basically, what is chemical kinetics? So when you talk about chemical kinetics, we are basically getting to study the rate of a chemical reaction. So how fast or how slow a chemical reaction progresses. So if you've been given reactants A plus B in a chemical reaction, giving us C plus D. And of course, in a case where we have got stoichiometric coefficients, you need to understand that the rate of a chemical reaction can either be given in terms of the reactants or the products. In terms of the reactants, we get to put a negative, then we'll say the change in concentration. For example, in this case, I can talk about A over the change in time. So of course, multiply by 1 over the stoichiometric coefficient A. That is also equivalent to negative 1 over B multiplied by the change in concentration of B over change in time. Then as you get to talk about the products, basically it's just positive. Okay, so why is it positive? Because we expect as the reaction progresses, we expect the amounts of the products to increase with time. That's why we need to expect that every time you are asked to determine the rate, it's basically going to be what? A positive value. Because when you're saying for a reactant, let's say I study that where the concentration of 2 molar concentration, then after maybe let's say a period of 10 seconds, after 10 seconds you find that the concentration reduces to 0.5 molar concentration. So you determining the rate of that equation, of course assuming maybe let's say it was 2A plus B. In terms of our A, our formula for the rate is going to be negative 1 over 2, which is a stoichiometric coefficient, multiplied by the change in concentration. The final one was what? 0.5. Initially we had 2 over the change in time, which is 10. So that is how you get to go about your calculations, where you're saying 0.5 minus 2 is going to be negative 1.5 multiplied by 1 over 2 divided by 10. So in this case, our solution is 0.075 molar per second. So these are the units that we get to work with when you're talking about the rate. Remember, for our concentration, it is molar. Then for our time, it is seconds. So the units are molar per second. Okay, so apart from that, under chemical kinetics, we also need to understand some of the factors that get to affect the rate of a chemical reaction. So of course, we did talk about, we've talked about some factors that depend on two theories. The first theory that they depend on is referred to as the collision theory. So when you're trying to understand how the factors get to affect the rates of chemical reactions, we need to understand that they are dependent on the collision theory. So this one tells us to say that for a chemical reaction to progress, or for chemical reaction to take place, what needs to happen is what? Particles must what? Particles must collide. So in every reaction, particles must collide with sufficient energy. So particles must collide. Not only should they collide, but they should collide with what? With sufficient energy. Okay. So when you're trying to look at the factors that are going to increase the rate of a chemical reaction, you're trying to look at how positively are they going to enforce or lead to collisions. So for example, when you talk about the increase in temperature, when you increase the temperature of reactants, do you expect to increase the number of collisions or not? So the more you increase the temperature, because we also understand that this is going to be dependent on kinetic theory. So you increasing the temperature will lead to an increase in kinetic energy of the particles, meaning that particles will be able to move more freely, and they will actually eventually get to collide more, leading to an increase in the rate of the reaction. So even as you get to talk about the concentration as well, you need to understand that when you increase the concentration of the reactants, the probability of the particles colliding is going to be more. So an increase in concentration also leads to an increase in what? Will lead to an increase in the rate of a chemical reaction. Talking about gaseous products, an increase in pressure. If you increase the pressure, of course, we do understand that pressure is inversely proportional to the volume. So the moment you increase the pressure, the volume is supposed to be reduced. And if you reduce the volume of a container, you expect that in a smaller container, with the same number of particles or with the same concentration, there are going to be more collisions in the smaller container. So increasing the pressure will also increase the rate of a chemical reaction. Then the other thing that we need to understand for the solid particles is the surface area. When you increase the surface area, you favor more what? More collisions. So an increase in the surface area will increase what? The rates of a chemical reaction. So those are some of the factors that we did talk about. Then one more thing that is very important is the formulas that we get to work with. So we call them the integrated ratios. So these apply to orders of reactions. So basically, what are these integrated ratios? So we need to understand that we have what we call first zero order reactions. So for a zero order reaction, the equation that we get to work with is basically the final concentration being equal to negative Kt plus the initial concentration. So on the graph, when you're trying to come up with a graph for a first order reaction, or when you get to plot the concentration against the time. So for a zero order, your graph is plotted, it's basically your time against the concentration of the particles. Okay. Of any particle, of any reactant. So when you get to plot your graph, concentration against time, if you look at our curve here, it is negative. So in this case, the gradient is negative. So if it comes out to be a straight line like this, that is basically it is proof enough that it's a zero order reaction. Alright. Then the other thing that we also need to understand is when you're trying to determine the, let me proceed to the first order. So when you talk about the first order on the other parts, the first order is basically going to be focused on the graph of time against the natural log of what? The natural log of the concentration. So that's the only difference there. So what happens is we are going to introduce the natural log to every part of the equation that at the concentration. Okay? But the gradient remains the same, meaning that if you plot the natural log against the concentration, if the graph comes out this way, it is also what? It is a first order reaction. Then for the second order reaction, instead of it just being with the natural log, it doesn't even have the natural log. So for the second order, what we basically have is the idea of it's basically one. It becomes the reciprocal of the concentrations. Okay, and here the gradient is a positive. So this one basically tends to face upwards. Okay, it goes this way when you plot it, when you sketch it. So it's very, very important in a case where they ask you to sketch. You need to understand that you try out different graphs. For the zero order, you try out the concentration just as it is given against the time. For the first order, you try out against the natural log of the concentrations. Then for the second order, just against the reciprocal of the given concentrations. So if it comes out to be a positive gradient, then you are clearly assured that what you have is what? Is a second order reaction. So now let's get to define what we have in this case. So the first question says, what is, or basically define the reaction rate. So when you're talking about the reaction rate, you're trying to look at how fast a chemical reaction progresses. Or you can define it in terms of the reactants, where you can say that the reaction rate is basically the rate of change of the concentrations of the reactants in respect to time, or per unit time. So now, that is generally speaking when you're talking about the reaction rate. So we also need to understand what the initial rate is, what the average rate is, and also what the instantaneous rate is. So I'll start with the instantaneous rate of a chemical reaction. So when you talk about the instantaneous rate of a chemical reaction, what you get to talk about is basically the reaction rate at any point. The reaction rate at any point in a chemical reaction. So the reaction rate at any point in the chemical reaction is what we call the instantaneous rate. It may be at start, it may be after 10 seconds from the starting point, or even at the end. So that is what we call the instantaneous rate of a chemical reaction. So now, thinking about this, we can move to what we call the initial rate. So the initial rate is basically the instantaneous rate at start, okay, or the rate of a chemical reaction just as you get to start. Initially, as you start. So the initial rate is the instantaneous rate at start of the chemical reaction. Then the average rate of a chemical reaction, on the other hand, is just going to be the rate of chemical reaction for a given period of time, or for a range. Okay, here you talk about the you're given the range or a period of time. For example, you say from 10 to 20 seconds. So you get to look at the concentrations at 10 seconds and at 20 seconds. So the rate of change of a chemical reaction between a range, or within a range, or within a period of time, that basically gets to tell you that that is the average rate of a chemical reaction. And that is how these are different. Question 2. A first order reaction is 38.5% complete in 480 seconds. Calculate the value of the rate constant. What is the value of the half-life? How long will it take for the reaction to reach 95% completion? So basically what we said is for a first order reaction, the equation is the natural log of what? The final concentration equal to minus Kt plus the natural log of what? The natural log of the initial concentration in a chemical reaction. So we've been taught that 8.5% complete. So at the start of the experiment, what you have is 100%. So that is your initial concentration. So now, after 480 seconds, it's 38.5% done. Meaning that from the 100 that you had, 38.5 has been used. So you subtract the 38.5 from the 100. And basically, if you get to subtract, what you're going to have is 61.5. So at final, after 38.5% is done, what you're going to remain with is the final concentration of what? 61.5%. So we have our final and our initial concentration. So now the question is, what can calculate the value of the rate constant? So it's just a matter of now plugging it into the equation there. Okay. So we have the natural log, the final concentration there. What we have is 61.5. So if I take the other on the other side, it will be a minus natural log. The initial we had 100 equal to minus k. Our time is 480. I've just substituted in the given equation there. So from our logs, we also taught subtracting logs with the same base is the same as you get the, or maintain the log, then you get to divide what is attached to the log. So this is the same as the natural log of 61.5 divided by 100 being equal to minus k multiplied by what? 480. So 61.5 divided by 100 is basically 0.615. So you have the natural log of 0.615 divided by, I can divide by minus 480. So at the other side, I can just remain with k. So I've taken away the negative together with a 480 and divided it the other side. So natural log of that divided by negative 480. So the result I'm getting for my k is 0.0010127. So that is our value for our k. So our final solution that we're going to present in relation to the given data there is going to be k is equal to 0.00101. So that is our value of k. Part B says, what is the value of the half-life? So remember, just before we get to present our value of k, we need to understand that every time you've been given the first order reaction, the units for k is S negative. Okay. So in a case where you've forgotten or you don't know how to determine it, I would advise you go by the retro. So when they tell you for to find the units for the constant k, what you need to look at is the basic concept on the retros. So I can come up with a retro on the first order reaction, meaning that it's only going to be dependent on a single reaction raised to the power 1. Okay, so like that, for example. So we need to understand that for the rate, it's basically molar per second. Then for our constant k, we don't know. For our concentration of the reactant, it's molar. So if you get to divide by the molar both sides, it's going to cancel out. And what you're going to have is that your k is going to be 1 per second, which is just second negative. That is how you get the units. So if it was a second order, it would just be what? To the power 2. And you would have molar per second, k, then your concentration would be squared, so it would be molar squared. So you divide by molar squared both sides, molar squared. So the molar would cancel out with 1, you remain with one single one there. Your k is going to be 1 over molar multiplied by second. So these are the units for second order constant, or it may be that if you take them on top or to the numerator.
If you want to have access to the entire solutions to this tutorial sheet, you can actually just register using the link in the description below. You have access to the solutions of this tutorial sheet and the ones in the past, including the past papers and also the videos teaching you the topics in full. Okay, this is available to all the other courses as well. Okay, so just do that.
Now, let's get to determine the value of the half-life. So we need to understand the formula for the half-life, which is basically determined from the integrated retro. So to just show you how it comes about, if you look at the first order integrated retro, it's a natural log of the final concentration equal to minus K2 plus the natural log of the initial concentration. So now your final concentration is like the half-life is like trying to ask you how long it takes for the initial concentration to be reduced to its half. So assuming initially our final or initial concentration was a 2 or maybe or a 1, whichever works, any of the two can work. So if your initial concentration is a 1, your half-life is basically the time it's going to take for that one to become what? To become 0.5, meaning that it has reduced to its half. So if you get to substitute in the equation, your final is what? 0.5 minus K2 plus natural log of what? 1. So then, remember we said from the natural logs or from the logarithm, from our logarithms we are told whenever you have a subtraction, so we can have subtraction of 0.5 minus the natural log of 1 being equal to minus K2. Remember the time that we're talking about here is the time it's going to take to reduce to its half. So we can just put it to be half there. At that point, these are same logs, so we can maintain the log, and then we get to do what? We get to divide 0.5 divided by what? 1. So from there, what do we have? We have equal to negative k t 1 over 2. Okay, so what we have now is 0.5 divided by 1, which is just like 1 over 2, or natural log of what? 1 over 2 being equal to negative what? Negative k t 1 over 2. Okay, so now at this point we also know that 1 over 2 is the same as what? Is the same as 2 to the power negative 1, which is equal to negative kT, which is our half-life. So our goal is to make the half-life to be the subject. What do we get to have? So logarithms tell us that can be dropped this side. So what do we have? The natural log of 2 equal to negative kt 1 over 2. So the negatives would go, and you remain with what? You remain with the positive. So your half-life is therefore equivalent to the natural log of 2 over what? Over your k. So this is our formula that works for the half-life for a first order. So equally, this applies to all the other orders of reactions that you may have. It's just a matter of you working with what you have to use it and determine the half-life formula. So now that we have our equation, we can now try to simplify it. Natural log of 2 divided by our constant 0.0101. What are we going to have? So natural log of 2 divided by 0.00101. So after doing your calculations there, after you've divided, I'm getting 686.28 seconds. So remember, for half-life, you're talking about the time. So the units are going to be what? The units are going to be seconds. So you can just say 686 seconds, because in the question we are given 3 significant figures. So that's what we have as our solution. Then the question also continues to say, how long will it take for the reaction to reach 95% completion? So 95% completion. So if you had started with 100%, then for it to be 95% done, you need to subtract the 95 from the 100 for you to be able to get your final concentration. So therefore your final is going to be what? 5%. So you can go back to our equation. The natural log of the final concentration, which in this case is a 5, is equal to minus k. Our k in this case is what? Is 0.00101 multiplied by the t, which is what we're trying to find, plus the natural log of the initial at start, which is 100. So we have the natural log of 5 over 100 from the logs, then equal to negative 0.00101 t. So 5 divided by 100 is 0.05. Okay. So we have the natural log of 0.005. So by the way, if you want, there's no need of you just trying to do what I've done. Or what you can do is just take this one and just subtract. Just say, punch it on the calculator as it is, as you have it. Natural log of 5 minus the natural log of 100. You're still going to have the same solution. So I was just trying to simplify it using the logs. So there's no harm doing that. So a natural log of 0.005 is equivalent to negative 0.00101. Then so natural log of that divided by negative 0.0101. And what I have is a 2,966.07 seconds. So looking at the first significant figures, this solution can even be 297.0 seconds. So that is still fine. And that's how you get to answer these questions. The third part of the question says, given the reaction rate data for that, determine the order of each reactant and the overreaction order. So This is a very good question which will help us understand how to determine the orders of reactions and also be able to come up with a retro when you're given such information. So it's like if we are doing three trials, three different experiments on the same reactants with different concentrations. So for example, if I talk about in the first experiment, we had that concentration of the fluoride, that concentration for the other reactant, and that was the rate. Again, you tried it out, you maintained the concentration for the fluoride, then changed the concentration for the other reactant. Then the rate changed. But in the other case, you tried to do the same. You changed the concentration for the fluoride and maintained the concentration as in the first experiment for the other reactant. Again, what did you observe? Again, you observed that even the rate was what? Changed. So when you get to do such, you're trying to understand, to see whether if you get to change the concentration of any of the reactants, does it have an effect on the rate? So we've seen in this case that in both cases, after maintaining any of the reactants concentration there, the rate was changing just after changing the concentration of any of the two. So therefore, we can predict that all these reactants have got an effect on the rate of a chemical reaction. So now we need to determine to what extent or what effect they do have by looking at the order. The way we get to do that is you write the ratio. So your rate is basically going to be dependent on K, which is a constant, multiplied by the concentration of the reactants that you have. And these are going to be raised to different powers. I'll say M and what? N. So A and B are just representing the different reactants that you may have.
If you want to have access to the entire solutions to this tutorial sheet, you can actually just register using the link in the description below. You have access to the solutions of this tutorial sheet and the ones in the past, including the past papers and also the videos teaching you the topics in full. Okay, this is available to all the other courses as well. Okay, so just do that.